So let's jump to the lightweighting example of this light aircraft direction pedal. So as Adam explained earlier, that the challenge here was to see the possibility of changing the material of an aluminum paddle to plastic paddle, right? So again, a typical example in the industry, on the left aluminum paddle, we did the stress analysis, and we found that the stresses were too low. So that means that a huge factor of safety. It means that the product is over-designed. So there was a huge margin to optimize, to change the material for a lower strength material and optimize the design. So this was the objective in this particular example. We wanted to minimize the mass. Of course, any mass that you can take off a flying machine will eventually make it more efficient. And the second thing, of course, to make sure that this paddle will still work as expected, was to see that the stress and displacement values were within the limits for the new design. The constraints that were given were to keep the same shape, of course, so that the pilot can put his feet inside. And the second was to reuse the same mold. So the outer shape or the molding shape should not change a lot. We were only allowed to put ribs so that we can create cavities in the existing mold. And that was, of course, a constraint to respect during the modification of this design. The given data was the initial geometry and the material, the initial material and the material that we intended to use, so the plastic, which was basically a fiber reinforced plastic, glass fiber reinforced plastic. And the second thing was loads and boundary conditions. So we had cables here, and we had a pin constraints here. So quite similar to what Adam showed initially with the brake paddle. So let's go quickly to the results with the analysis. Of course, of the force of around, I think, 16 kilogram, which is basically the braking force or the paddling force, was applied in both scenarios. So first on the left was the aluminum. Again, we figured out that the stresses were too low for the aluminum, so a high factor of safety. That means that it was feasible to change the material to something less stronger, so plastic, which has a lower yield strength, but still with the lower stresses, which were around 10 megapascal, the factor of safety was within the acceptable limits. And the last image here on the bottom you can see is the displacement contour, and the displacement were, of course, a little bit higher in case of plastic as compared to the aluminum version, but still they were below the expected limits. So this was an iterative design process. We used the modeling tools inside Inventor to add ribs, and then did multiple iteration to come up with the optimal rib design. But of course, such type of simulation can be done parametrically, where you can define some intelligent model with parameters of rib placement or rib thickness, and launch multiple number of parametric configuration to come up with an optimal design automatically with Inventor optimization tools. So this is here a comparison of the percentage improvement of different parameters between these two configurations. The first one is the most important parameter of weight, where we see that we were able to optimize or reduce the weight by 50%. The cost was reduced with the plastic version against aluminum version by around 29%. The embedded water saving were 74%. Carbon footprint reduced to 48%, embodied energy 47%. So we have more details on our website, and maybe Adam can add more details about this.
Yeah, so these results came from the Inventor Eco Material Advisor, which is a tool within Autodesk Inventor. So it's kind of cool to see how you can use simulation in conjunction with these with the Eco Material Advisor, for example, to see after you make a design change, how much of an impact it will have towards the embodied energy or the carbon footprint of a part. So thanks, Shakeel. There's a lot. That was a lot of information. We wanted to sort of show an example where different types of simulation could be used to help solve a complex problem. And so that heat exchanger example, as you saw, had fluid flow, had heat exchange, and had stress analysis. And so, but fundamentally, a lot of the same processes applied in terms of wanting to do iterative design changes to optimize a part. And so you can learn how to do this on your own projects. We have resources available at the Sustainability Workshop at engineeringexploration.autodesk.com as well, has some in-depth tutorials on simulation multiphysics. And SimSquad has some great resources. They have a simulation TV channel that talks about simulation topics and the different simulation tools within Autodesk. You can get in touch with us at ecoworkshop@autodesk.com if you have specific questions.